So in this video, we're just going to briefly look at this solution to the last problem. We have three cables that are suspending a plate that has a known weight, and we want to compute the tension in each of these cables. So this is just an equilibrium problem in 3 dimensions. Like all equilibrium problems, you want to start out by drawing a free body diagram. We have forces that have an unknown magnitude but a known direction corresponding to each of the tensions. Since they're suspended to the ceiling, we know they go along the y-axis, so these will be in the j-hat direction, but each will have unknown magnitudes, Ta, Tb, and Tc. And we know if we're given the weight of the plate that we should draw its point of application, assuming its uniform density at the centroid of this area. So if it is 4 inches wide and 6 inches deep, I'm going to put it 2 inches along the x-axis and then 3 inches along the z-axis. So we will need all of that. And in terms of how you actually go about solving this, the most efficient way to do it is to begin by enforcing rotational equilibrium about one point of which the cable is connected, because that's going to give you, and as long as you do it amongst B or A initially, you'll get a system of equations where you can solve for 2 of the 3 unknowns. And once you have 2 of the 3 unknowns, you'll be able to solve for the third by simply enforcing vertical equilibrium or summing all forces in the y direction. So I'm going to begin by determining rotational equilibrium about point B. So I'm going to sum all moments about point B. So how do I do that? Well, let's just go step by step. What is the moment that the unknown tension acting at A exerts about B? Well, I need to draw a position vector from B to A. Notice that a position vector from B to A, it doesn't go any in the x direction. It doesn't go any kind of out along the way that my mouse is showing. It doesn't go any up or down. The displacement from B to A is purely in the z direction. So notice that that position vector is just going to be 4k hat. And what are we crossing with? Well, we don't know the magnitude of that force, so I'll denote it as TA, but I note that its direction is along the y-axis, so it's a j hat. Now let's compute the moment of the weight about point B. How do we get from point B to the centroid of this plate? Well, we do have to have a displacement in x. How much is it? Well, if it's 4 feet instead of inches, 4 feet across, I would go halfway over, so that's just going to be 2 feet. And I also have to go sum out in z as well. You notice this is all kind of a planar problem along the y equals 0 plane. But B is already 1 foot out, and the centroid, since this is 6 feet in depth, is going to be 3 feet out. So I need to go an additional 2 feet along the z-axis or in the k direction. So that's where this 2i hat, I have to go halfway across the plate to the right, and 2k hat, I have to go 2 feet more out along z is coming from. And I do know the weight. I just using a placeholder w for now, but it is directed along the minus j, along the minus y-axis, which we denote as minus j hat. Finally, in order to compute the moment of the tension at point C about point B, I need to draw a position vector from B to C. I need to go all the way across the plate, which is along the x-axis, so it's going to be 4i hat. And then in addition, since B is only 1 feet out and C is 2 feet out, I need to go an additional foot out along the z-axis, so that's where that 1k hat is coming from. So all the way across the plate, 1 more feet out in z, and I don't know the magnitude of this tension either. However, I do know it's directed in the j-hat direction. Now what we want to do next is compute all of these cross products and see if we can set up a system of equations that we can actually solve. And what we're going to remember is this unit circle for computing cross products here. Namely, when you take cross products of unit vectors, we can determine the result. It's going to be another unit vector in general, and the question is whether it's positive or negative. And if you look at whatever 2 cross products, whatever 2 unit vectors you're trying to take a cross product of, just see if in the circle you're moving clockwise or counterclockwise. And if you're moving clockwise, the result is positive. If you're moving counterclockwise, it's negative. So for k hat cross j hat, there's k, there's j, and going from k to j, I'm going counterclockwise. I'm going against the direction of these arrows. So k cross j is actually going to be negative I. So that's how I'm getting when 4k hat cross t sub a j hat, k hat cross j hat is negative I hat, and then you have your 4TA term. Now let's try the same thing again here, but realize that you're going to basically have a distribution. You're going to need to take the 2i hat, cross the minus j hat, and then the 2k hat, cross the minus j hat. So let's do 2i hat cross minus w j hat first. Remember, I hat cross j hat is just going to be k hat. We're moving in the clockwise direction, so put the k hat there, and that's just going to be 2 times minus w. So that's where it's going. It's becoming minus 2 w k hat. K hat cross j hat, Notice we're going in the counterclockwise direction. That's going to give us an I. So we're going to have a minus I. But don't forget, it's 2 times minus W. So the minus times minus becomes plus. It's just 2W I hat. I'm sure all of you know how to do this by now. So just compute that last distribution as well. You have to do 2 more cross products. Combine like terms. You have some terms that are along the I hat component, and you have some terms that are along the K hat component. The good thing is along the K hat component, you only have one unknown. You only have the the tension of the cable at C, because you do know W. So in order for any vector to be 0, all of its components have to be 0. Set this equal to 0. So to solve for TC in terms of W, that should give you 32.5 pounds. Once you have TC, set the I hat component to 0, and you can solve for TA. That'll give you 24.375 pounds. And then if you sum all forces in the y direction for vertical equilibrium, you know that whatever portion of the weight that TC and TA aren't already overcoming, that has to be consumed by the tension associated with cable B. So that's how you can determine the tension in cable B. So hopefully that gives you a good idea of how to go about solving that last problem, and best of luck on the test.